Hi, everybody. Welcome back to another FLAN seminar. Today we have Thomas talking to us about Ehrenfeucht-Haussler rank and chain of thought. Take it away.
Thanks. This talk summarizes some results that unfortunately are not yet published in any form. There is no archive paper even, but I hope we'll have it out in the next 2 months. And this is joint work with Pablo Barceló and Aleksander Kozaczyński. So as a for warm-up, as a kind of motivational example, suppose we have a large language model and we ask it to do some composition task. So we have this query on the left, where we have some relation of being an advisor. Advisor of Alice is Charlie, advisor of Bob is Dave, and so on. And we want to ask about the composition of this relation. So like, who is the advisor of the advisor of the advisor, and so on. And since the models now are trained to output chain of thought answers, by default, this model does it, and thanks to that, it's able to give us a correct answer by first, looking at who is the advisor of Alice, Charlie, who is the advisor of Charlie, and so on. However, if we try to, we can easily force the model to make a mistake by asking it to just give us the answer. And somehow in this case, the model gives us the wrong answer. And I think if we do this on ChatGPT, it will also give us the wrong answer. So of course, there may be different reasons for this behavior, but some possible explanation would be to say that some tasks are just too hard to be solved in one iteration, and we really need to have several iterations and break some task into a chain of thoughts. And yeah, so somehow, so some tasks maybe introducing these intermediate tokens is important. And we can ask, well, what task can be computed using exactly R tokens, and which cannot be computed using, for instance, R-1 tokens, intermediate tokens. And there is some previous work where using this intermediate tokens is very important. For instance, this result on Turing completeness heavily relies on the fact that we are able to produce these intermediate tokens, in fact, in unbounded manner. So in this work, we will give some characterization for a very simple model of one-layer decoders with unique hard attention, and it will be also non-uniform. Let's say that already. So so we are all on the same page and we agree on the definition. We have this this model that maybe have several heads in one layer, and we'll be thinking that the last token attends to other tokens and with some attention, and we just choose we choose the information from the token which maximize the attention, and if there is more than one, we choose the leftmost. And then after that, we have some multi-layered perceptron that perhaps does something more on what we got from attention, and then we use this to produce a new token. And of course, we can iterate this process to produce yet another token by doing the same thing with the extended sequence and so on. And we want to think that after r iterations, what we have on the last token is supposed to be the output of some function that works on the tokens u1 to un. To be a little, there is one specific thing that in what I'll be talking, we assume that the input, like if you want to compute a function of n arguments, our input will be actually n of length n+1, because we assume that we also finish the input with some kind of special end of the input symbol. Again, this is what we'll be doing. This end of the sequence token will be attending to all the others. So to the input of the function, we'll be producing new tokens. And then after some fixed number of iterations, we want to obtain the value of a function with arguments x1 to xn. And for instance, for the case of composition, so suppose we have a threefold composition, and let's consider like a very, very special variant of this composition. So I was thinking that I have as an input an Ri, which gives me the value of f given 1, given 2, up to some number n. And the function that I want to compute is just f of f of f of 1. So if it's for threefold, I mean, if it's twofold, of course, it would be f of 1, and so on. And well, so even before going to the transformer, how we would like to use this input to compute f of 1. Well, first we would probably look at f of 1. This gives us some value. Let's assume also for simplicity that these values are all inside, all bounded by n. So first we would probably take at f of 1, this would be some k, then we'll go to k token to check the value of f of k. This again would give us some another token, we would check that token, and after many iterations we get to what we want. And we can do that with hard attention and transformer, and somehow what we want to have is that, well, we have these values f of 1 to f of n given as input. We do some positional encoding. So we encode these values with some positional encoding, and we probably want to first produce, like in first iteration, we'd like to produce something that just reads the f of 1, and this is our new token. Then we want to, in the next iteration, to read the value of the iterated value. And finally, we get to the third iterations, and this is our output. So what's the characterization that is some of the main results is that we can characterize the functions that can be computed in r iterations in this one layer decoder model with unique hard attention by rank Ehrenfeucht-Haussler rank of decision trees. And well, what does it mean? So first, decision tree, it's something like that in the full generality. I guess for originally for binary inputs, this could be something like that. First, we will look. It's an algorithm which tells us, okay, if the value in the first bit is 1, then ask something. If it's 0, then ask something else, and then we check the values. And in the end of this tree, we follow the path according to what we see on our input sequence. And in the end of the tree, there should be an answer to the function. And the rank is usually defined by this recursive equation. So it just if you have yeah, okay, so yes, okay, so this is actually, I guess you don't need to understand that. What's maybe more important is that we can think about a different variant of decision tree, so which already makes sense for, okay, so I mean, because if you would like to, I want to talk about functions which maybe are not Boolean. And then one idea to move from these binary trees to decision trees for non-Boolean functions would be, okay, we have non-binary trees that can be maybe branching more than twice, but then this might become kind of unhandy. So we do a little different trick to stay still in the world of binary trees. We will have the tree where the nodes are labeled with assignments. By assignment, I mean, well, in the position I, the value is, for instance, B. And we can think that this is a question, and then the tree branches into children. The first children corresponds to an answer yes, and the second children corresponds to answer no. And we can observe that then the rank in this tree, I mean, something that's equivalent to the to how the rank is normally defined, is just the maximum number of the yes edges in all the paths. And what I mean, somehow what we want to think is that also each iteration of our decoder corresponds to answering yes in this tree. On the queries on is this assignment true? Okay, so maybe let's go to the proof so you can get some more feeling of what is really going on. So first, I want to argue or give you at least a sketch of the argument how we can go from the decoder to the decision tree. So we suppose that the function is computed in early iterations with this one layer decoder. For now, let's just limit our attention to one head. Suppose that this is true. So what does it happen? In first iteration, as I said, we take our this special symbol, special token that marks the end of the input, and this token has some attention to all the other input tokens. So we can think that we have some ordering on the different possible assignments that our input can have. And well, if there is some assignment that gets maximal possible attention, if this assignment is true, then this maximal possible attention will be exemplified in our attention layer. And this is exactly the token. The token corresponding to this assignment will be the one that we'll get the information from. If this assignment doesn't appear, then that means that some argmax is somewhere later in this ordering. So we can think that if we order by all these assignments by how much attention they can get in our transformer, perhaps also if there are some assignments that have the same attention, we also then order them from left to the right, and we get an ordering of the assignments. And from this ordering of the assignments, we get a tree. We can construct the tree. Remember, our decision tree was supposed to have in the nodes questions assignment. Is the value in I position A? Yes or no? So again, if this is true, if xi is equals A, that means that our maximal attention is concentrated on I. Sorry, if xj is equal A, then our attention is concentrated on token J. So depending on how what is the argmax in our model, this tells us whether given assignment is true or not. And then we can glue together these little trees that we get for next iterations and obtain the full tree that computes the same function as our one-layer decoder. And okay, which is perhaps a very important detail, as I advertised earlier, the rank, we can think about the rank as the number of maximal number of yes answers in every path. So indeed, if we glue together these trees obtained from each iteration, that means that in every path we'll have exactly as many iterations, I mean, as many yes answers as iterations. So the tree that we are obtaining has the rank corresponding to the number of iterations that we needed in the first place to compute this function. And now for the proof in the other direction, so we start with the decision tree, and we want to make a transformer out of it. Somehow the idea is maybe similar, but we have to just invert it. Okay, so suppose that we are in some node alpha after t iterations, after t answers, after we are going in our tree and we have counted t yes answers, and we are in some node alpha which corresponds to this xj equals a. And now on our inputs we go down and end up in some node beta after t plus 1 yes answers. So we want somehow our transformer decoder to mimic that. What we want to obtain is that in these new tokens that these intermediate tokens that we are writing on the right to our sequence, we want to encode where in this tree we are after given iterations. So first, we'll think that this end of the first we have like the last token is the special end of the input token, and we can think that it's the positional encoding that will apply to it will somehow correspond to being in the root of the tree. Then we want the transformer to look at our inputs and tell us where, by reading this input and going using the tree, by following the tree guided by the input, where is the first yes that we encounter. And we want to extend our tokens by a new token that will encode the position of this first yes. So this will be some node below the root. And then after every iterations, we get lower. Since our tree has bounded rank, some rank R, there is always at most R yes answers, and after R answer we get to the bottom, to the leaf, and we get an answer to the function. And again, to do that, we want to have we need to use some tricky positional encoding. So well, like if you're a logician, then perhaps it's somehow clear that a tree is also an ordering. So we can think that the paths in the tree correspond to some ordering on the assignments. So if we have on the input in the, for instance, first position some value b, then our positional encoding, well, first it will be encoding this information that this is the first position is b, but also it will be encoding, it will have for each node in our tree, it will have a separate coordinate, which will encode starting from a given node, how many steps I need to do in the tree to get to a node asking the question x1 equals this value, the value that I really have in my token. And then somehow my attention will my attention layer will be trying to we want to construct our transformer in such a way that it will maximize the attention in the starting from a assignment alpha that's encoded in the last token, which that's the attention is maximized on the input token, which corresponds to the first true assignment below the node alpha. So in the case of this example, we want to have something that, okay, after t iterations, we are in the node alpha, and the first true assignment in our input is this assignment xl equals c. So we want our attention to be maximized on the ELT token, which is equal C in our input. And then we will be wanting to do some simple linear transformation to produce a new token, which will, again, in a hot zero hot manner encode the information about in which node we are. So this is somehow the very raw idea of the proof, and perhaps I'm omitting some important details there, but it's nothing very hard or unusual what's happening there. And now, okay, so this first theorem that I presented was somehow for one head, because okay, if we have normal tree, then it's somehow very natural to map it to one attention head with third attention. But we would like to have more, so we would like to understand what's going on with multiple heads. And to obtain that, we introduce some generalization of the notion of rank, which we still call decision tree, but I guess it's not longer exactly a tree. So we think again, so as I said, we can think about the tree that it's some kind of order, we get orderings on the assignments, which these orderings that tell us in how we should ask the questions, is this assignment true? Is this assignment true in what order? So now in this multi-head decision tree, we just, instead of having like linearly one ordering, we have H somehow independent orderings, and we go through them in a parallel manner until in each of these orderings we encounter the yes answer. So we find the first assignment that is satisfied in our input. And this is the first iteration. Then using the information of where we stopped in each of the orderings, we go to the next ordering, next H orderings, until we encounter R yes answers, and the output is produced. I mean, I suppose this looks awful, but the idea is relatively easy. It's just very simple generalization of what's going on in the normal tree. Okay, so in the end, we have the full power of our result is that for any H and R, a function which can be computed by R iterations of one layer decoder with H hard attention heads. A function can be computed in that many iterations if and only if it can be computed by rank R decision tree with H heads. So with H parallel orderings on assignments. And we have some applications. So maybe first this. So we started from our motivation was this example with composition, and remember we have observed that if we have t-fold composition, then then yeah, t iterations should be enough because we just first look at the value of f of 1, then look at the value of f of 1, and so on. But we want to understand, is t the best we can do? Perhaps for t composition, there is some procedure, some transformer that can do that with t minus 1 iteration. And as it turns out, at least for this simple case of one layer with hard attention, no, t is exactly the best that we can hope for. And well, I mean, I guess perhaps the proof, the idea of the proof would be maybe said without going into any of these details. Of course, the proof is via decision proofs using this main result. Somehow, if you think what could happen that we are able, so what would need to be guaranteed so that we can somehow compute the default composition in in less than t iterations? Well, that would mean that there is some cycle in the function. So there is some f goes, I don't know, f1 goes to k and fk goes back to 1. Then already we have to read this input table less times than the number of compositions would suggest. But then if the input is large enough, then we can always construct examples where there is no cycle, and basically this is like very very like intuitive idea of what's going on in the proof. So we know already by our examples that to solve this task we need to do t iterations of transform of the coder, and we also try to see. No, okay, because you can say, yeah, maybe that's not very interesting because it's only one layer, and also it's hard attention, and the real models are with softmax, so who cares? So we try to train a simple model with softmax, and well, we try to compare. Well, first we train the model to solve our tasks with as many iterations as the theoretical results suggest, and then we try to do that with one iteration less. And indeed, we see very nice separation. So on the right, we have the empirical error and validation error. This is threefold composition already and 3 iterations. You can see that it goes to 0 relatively quickly. And on the left, we have 2 iterations. And even though we have more heads, it doesn't matter. We are not even able to minimize the error on to obtain even the empirical risk minimization. And this error is just the absolute value between what the transformer outputs in the last token and the value that the function, the composition gives us. So it seems that at least this results has some resemblance in in real models, in what happens in real models. But of course, it would be interesting to see if we can somehow generalize this characterization for, I don't know, more layers or softmax. And finally, as an aside, these decision trees were studied from the perspective of pack learning, and in particular, there are some results that are, of course, not ours, but well, so one thing that we can observe is that since the decision trees can be improperly learned in polynomial time, then also this one layer transformer can with that many iterations. And we could ask, well, what about proper learning? So, okay, let me explain myself very briefly. I guess I don't have time to define pack learning for very precisely, but let me just say what's the difference between proper learning and improper learning. So the proper learning is the case where we are supposed to only output functions in the class. So if I say proper learn functions of h head rank at most r, that means that my learner is only allowed to output this kind of functions. And improper learning means that I assume that my true function is of the form h head rank at most r, but I'm able to output different functions outside of this class. And we have this result that tells us that for this multi-head rank are ready for two and ready for two heads and small rank, very small rank. We cannot properly pack learn that in polynomial time. Well, unless some standard cryptographic assumptions are false. And I guess that's all I have prepared for today. And if there are any questions, I would be happy to answer. And if I don't know, probably my friend Sasha here who will help me.
Is is that a clap or is that a I have a question? I saw like a hand go up, but I don't know if that was a clap or a question.
It seems more like a clap.
Oh.
Yeah, that's a clap.
Oh, okay.
Well, thank you then.
Um, can you go back like to the empirical example that you gave? Yeah,
Here, yeah.
can you explain, sorry, what was actually learned here? What was the actual task here?
So this is this decomposition which we interpret like that. So on the input,
Oh, okay.
I have values of some function f, f of 1, f of 2, f of 3, and so on, up to some n. And what I want to have on the output is f of f of f of 1.
Okay, got it. Then I think that we'll end the recording here and then we'll have a longer question session.
Sure.
Thank you.
Thanks.